In the last class, we were discussing about the deadlock prevention algorithms, and we have said that the deadlock prevention technique tries to see that one of the four necessary conditions for the deadlock occurrence does not occur. So the four necessary conditions are mutual exclusion, hold and wait, hold and wait, then no preemption, and the fourth condition is circular wait. So we have already discussed about that the mutual exclusion in some cases may not be possible to avoid because there are some resources which are by nature non-shareable. Hold and wait can be avoided by following some protocol for request of the resources. Similarly, no preemption can also be avoided. In case of circular wait, we have said that to avoid circular wait, we define some mapping function, say f, which maps the resource types, set of resource types R to the set of natural numbers n. Okay? And we have said that a process, while holding an instance, one or more instances of a resource type Ri, can put a request for another resource type Rj only if f of Ri is less than f of Rj. Okay? So while holding resource type Ri, a process can put a request for a resource type Rj only if f of Rj is greater than f of Ri. Okay. So if we follow this, in that case it is possible to avoid the circular wait condition. Let us see how. Suppose in a system we have got n number of processes which are working at a time, and the processes are, say, P1, P2, P3, like this, we have Pn. Okay? And we assume that process P1 puts a request for a resource type, say, R1, which is currently allocated to process P2. Process P2 puts a resource type R2, which is currently allocated to process P3. This way it continues. Process Pn is holding a resource type, say Rn minus 1, and this Rn minus 1 is requested by process Pn minus 1. Pn in turn is requesting for a resource type Rn, which is currently allocated to the process P1. Okay? So this is our circular wait condition, in which case none of these processes can complete because every resource which the process wants, that is held by another process, which in turn is waiting for another process to be released by the next process in the sequence. Okay. So this leads to the circular wait condition. Now following this limitation, that a process while holding a resource of type Ri can put a request for a resource of type Rj only when f of Rj is greater than f of Ri. Now coming to this condition, you find that process P1 is holding Rn, and it is putting a request for resource type R1. So the condition that must be satisfied is f of R1 must be greater than f of Rn, because process P1 is holding Rn, and while holding Rn it puts a request for R1. So f of R1 must be greater than f of Rn. Similarly, process P2, while holding resource type R1, it puts the request for resource type R2. That means f of R2 must be greater than f of R1. And if you follow this, process Pn, while holding Rn minus 1, it is putting a request for resource type Rn, which indicates in this sequence f of Rn must be greater than f of Rn minus 1. Okay, so all these conditions must be true. Now, if you follow the transitivity, you find that this leads to a condition, and similarly, process P1, while holding Rn, it puts a request Rn minus 1, so this condition must be true. And here, following transitivity, you will find that we lead to a condition that f of R1 must be greater than f of R1. Okay, if you apply transitivity to all these relations, it leads to such a type of condition that f of R1 must be greater than f of R1, which is not possible. Okay, so if we impose such a condition that a process holding Ri can request for a resource Rj only when f of Rj is greater than f of Ri, in that case, such a circular wait condition will never occur. Okay, and hence there will be no deadlock. Now the condition is, question is how to design this function f or mapping f. So whenever we decide the nature of this f, we have to see that what is the natural sequence in which the processes usually request for the resources. Okay, so normally at the beginning the process will request for some input device, that is the resource. In between, it may ask for some storage devices, and then finally it will ask for output devices. So normally what will be followed is the mapping function f of the input device will be less than f of the storage device, which will be less than f of the output device. Okay, that is, while holding an input device, the process may request for a storage device. Okay, while holding the storage device, the process may request for an output device. Similarly, while holding the input device, the process may request for an output device. But while holding the output device, the process cannot put a request for the storage device or cannot put a request for the input device. For doing that, the process must first release the output device, because that is having the maximum mapping functional value. So first the process will have to release the output device, then only it has to put a request for the input device. Now if the output device is required again, then the process has to put a separate request, a fresh request for the output device at some later time. Okay, so if you follow such a condition, such a restriction, in that case you will find that this circular wait condition will never occur, and because the circular wait condition will never occur, so I will never have a deadlock in the system. Okay. However, it is not always possible to follow that restriction, because you don't know in which order the processes may request for the resources. So if we strictly follow this, in that case it may lead to poor utilization of resources. Okay. So to take care of that, the other type of technique for dealing with deadlock, which is called deadlock avoidance technique. Okay, in both the cases, whether it is deadlock prevention or deadlock avoidance, we are trying to see that the deadlock does not occur in the system. Okay, so one of the ways is deadlock prevention, which tries to eliminate one of the four conditions which are responsible for the occurrence of deadlock. And the other type of approach, that is deadlock avoidance approach, does not put any such restriction on the way the processes will request for the resources. But it assumes that processes can request for the resources whenever they like and in whichever order they want. We don't want to put any restriction in the way the resources will be requested. So whenever the process puts a request, it is the system which will decide whether that request can be immediately met, depending upon the available resources and the way the resources will be released by the processes which are already allocated. Okay? So the system will do some background calculation, and based on the output it will decide whether the request can be immediately granted. If it is not immediately granted, the process will be requested to wait. It will be asked to wait until and unless some more resources are made available because of release of the resources by the processes which are complete. Okay? So when some more resources are available, then only that request can be met. Okay? We'll see the algorithm. So this is an approach which is called a deadlock avoidance approach. So what we'll talk about now is deadlock avoidance. So naturally, in case of deadlock avoidance, because the system has to do some background calculation to see how the resources are going to be released by different processes, so it is better that every process in advance declare that what is the maximum requirement of the process. Okay. So it is not necessary that the processes will acquire it before initiation of the execution, but the process has to at least let the system know that so many instances of such resource type will be required by the process while execution. Okay. So in advance, every process has to declare what is its maximum requirement. Okay. So if that is known to the system, now it is possible for the system to see whether the resources can be allocated or not. Take the simple example. The first example, in case of deadlock, we have said that we have two processes, P1 and P2, and we have suppose two resources, one is resource A and another is resource B. Both the processes P1 and P2 need both the resources for completion of their work. Okay? And we have said that if we have this kind of situation, that process P1 first puts a request for resource A and it gets resource A. Process P2 puts a request for resource B and it gets the resource B. In this situation, process P2 puts a request for A, which is held by P1, and P1 puts a request for B, which is held by P2. So this leads to a deadlock condition. Okay? Now, if we do it this way, both processes P1 and P2, they declare that they need both the resources A and B for completion of their work. Okay? So whenever process P1 puts a request for A, P1 gets A. Next time when process P2 puts a request for B, system knows that this B will also be needed by A, because both P1 and P2 has declared their maximum requirement. So now the system knows that though P2 has put a request for resource B and the resource B is available, but P1 for its completion needs the resource B. So what the system can do is, the system will ask P2 to wait. Even if B is available, it will not be allocated to process P2, because that may lead to deadlock. So it will ask process P2 to wait. Next time when P1 puts a request for B, B is allocated to P1. Now once B is allocated to P1, P1 gets both the resources A and B. Okay? So it gets both the resources and P1 will be complete. On completion, P1 will release both A and B. Only when both of them are released, then only P2 has put a request for B earlier. Now B can be allocated to P2. And subsequently, A can also be allocated to P2, and P2 can also complete the operation. Okay. So this way, If the system knows that what is the maximum requirement of different processes, it can decide at what time the resources can be allocated to the processes. Okay. Now, we will see formally an algorithm which will do similar kind of task. And this algorithm is known as Banker's algorithm. Okay. So, we will talk about the Banker's algorithm. Now, this algorithm makes use of a number of data structures. We assume that there are n number of processes in the system, and m number of resource types. And as we have said, that every resource type can have a number of identical instances of that resource type. So, there are n number of processes and m number of resource types. Okay. Now, the data structures which are used by this Banker's algorithm, one of the data structure is a vector of dimension m, and we call that vector as a vector available. It is a vector of dimension m. Okay. So, if available I is equal to some value, say k, that means that k number of instances of the resource type I is currently available. Okay. The second data structure that is used by the algorithm is the data structure max, and this is a matrix of dimension n by m. That means this is a matrix is having n number of rows, one row for every process, and m number of columns, one column for every resource type. Okay. And here again, if max ij is equal to some value, say k, that indicates that process pi requires maximum of k number of instances of resource type rj for its completion. Is that okay? So, as we said, that every process in advance has to declare that what is the maximum requirement of resources. So, that maximum number of maximum requirement of resources for every process is put in the form of a matrix. Okay. So, for ith process, the maximum requirement is a row vector. Okay. Where every element in the row vector will indicate that for which resource type, how many instances of that resource type is required by the process I. Okay. Then the third data structure that the algorithm uses is allocation. Allocation again is a matrix of dimension n by m. Okay. And here this indicates that how many resources of which type are allocated to different processes. So, if I say that allocation ij is equal to k, that means k number of instances of resource type rj is currently allocated to process pi. Okay. It also uses another data structure, of course, that can be generated from max and allocation, a data structure which is called need. Need is again a matrix of dimension n by m, and this indicates that what is the future requirement of different processes. Okay. So, if I say that need ij is equal to k, that indicates that k number of instances of resource type rj will be required by process pi in future. Okay. So as I said, that need can be computed from max and allocation because the process has declared the maximum requirement, and this allocation tells you that out of that maximum requirement, what is the number of resources that are currently allocated. So obviously the remaining number is the matrix need. So naturally, need is the difference of max and allocation. So if you know max, if you know allocation, you can compute what is need. Okay. And for this algorithm, we also assume that if x and y are two vectors, okay, in that case, we assume that x is less than or equal to y if every component of x is less than or equal to the corresponding component of y. Okay, so that is how we define the less than or equal to relation for between two vectors x and y. Okay, so using this, now we can write the Banker's algorithm for deadlock avoidance. The algorithm will be executed whenever a process puts a request. Okay, and we assume that the request is also put in the form of a vector. Because there are m number of resource types, so whenever the process puts a request, it will put request for the number of instances of different resource types. So even the request can be put in the form of a vector, can be represented in the form of a vector of dimension m, where every element in that vector will indicate how many instances of the corresponding resource type are requested. Okay, so we assume that whenever a process puts a request, a process pi puts a request, and that request we represent by a vector called request. And I say that this is a vector I. That is the request vector for the ith process. Okay? And then the algorithm will work like this. So now let us see what will be the algorithm. Whenever a process pi puts a request, then the request can be met only when the request vector request I is less than or equal to available. Available tells you what is the number of resources of different types that are currently available. So if request I is not less than or equal to the available resources, then obviously the request cannot be met. So the process has to wait. Okay? We can think whether to allocate the resources or not only when request I is less than or equal to available. Okay? So the first condition that is to be checked is whether this request I is less than or equal to available or not. The another condition that has to be checked is whether whenever a process has put a request, whether this request vector contradicts the maximum requirement that has been declared by the process. If it contradicts that, then this request cannot be honored. Okay? So first we'll see whether this request is a valid request. That means at a particular instant of time, the process has got certain resources. Okay? And in the need matrix, we will know that what is the future need of the process. So always our condition should be that whenever process puts a request, the request vector must be less than or equal to the corresponding need vector. If it is greater than the need vector, then this request is not a valid request. Okay. So the first thing that has to be checked is if request I is less than or equal to need I. When I say need I, that means it is the ith row in the matrix need. Okay. So if request I is less than or equal to need I, then only we can process this request. So we'll say that then go to step 2. Okay. Else, the process has exceeded its maximum requirement, so you have to give an error message. Okay. So that is what you have to check in the first step. In the second step, when you come to the second step, then it is sure then that the request is a valid request. Now we have to check that whether this request can be immediately granted or the process will be asked to wait. Okay. So second check that you have to make is if request I is less than or equal to available. As we said, that available is a vector which indicates that how many instances of which resource types are currently available. So this request we can think of granting only when request I is less than or equal to available. If request I is greater than available, though it is a valid request, the process has to wait. There is no other way. Okay. So if request I is less than or equal to available, then we go further. So then go to step 3, and if request I is greater than available, then you have to wait. So we put else wait. Pardon? No, available is a vector. It is not a matrix. Available tells you available is not a matrix. It is a vector of dimension m. Whereas we have put it as need I because need is a matrix. Need is a matrix. And when I say need I, that means it is the ith row in the matrix. Okay. We have said request I because it is the request vector put by the ith process. But available gives you overall number of available resources at a particular instant of time. So that is a vector, it's not a matrix. Okay. So if request I is less than or equal to available, then we proceed further, else the process has to wait. Okay. Then in step 3, what we do is, we have seen in step 2 that the request is less than or equal to available. That means the system is in a position to meet the request. But now it has to decide based on some analysis that whether this request will be safe, whether this allocation will be safe or it will be unsafe. Okay. So for that, what the system will do is, the system will pretend as if the request is immediately granted. Okay. And that is where this data structure comes into picture. In step 3, the system pretends as if the resources are allocated. And that can be done by simply modifying the data structure. Okay. So if I grant this request immediately, in that case, what are the data structures that are to be modified? The first data structure that is to be modified is available, because available will now be reduced by this request. Okay. Next data structure that is to be modified is allocation ith row in the allocation matrix, because now the allocation will also be changed. That has to be added by this request. And the third data structure that is to be modified is the need, because now need will be reduced by this much amount. Okay. So you make available is equal to available minus request time. You see that I am only modifying the data structure. The resources are not physically allocated. Okay. Then allocation I, because allocation is a matrix, and we have to modify the ith row in the matrix. So allocation I will be allocation I plus request I because the request is apparently made, so allocation, the corresponding elements in the allocation will also be increased. Okay, and need I has to be need I minus request I. Okay, so this is a pretension, it is not the physical allocation. So we will write the system pretends to have allocated the resources. So this is not the actual allocation. Okay. So after doing this, what we have is the system moves from one state to another state. Now we have to see that whether this new state that is arrived, whether this is a safe state or not. Okay. Now when I say that a system is safe, that is if I find that with the available number of resources, all the processes can complete in some arbitrary order. It is possible that I will still be able to manage the execution of all the processes. That means all the processes can complete in some arbitrary order. Then we call this state to be safe state. Okay. So in order for a state to be safe, there must be a sequence of the processes in which they are able to complete their execution. But it is not necessary that that is the actual sequence in which the processes will be completed. But there is a way, there is a sequence in which the processes can complete execution. And such a sequence is called a safe sequence. Okay. So here we will see that whether this new state is safe or not. Check if this new state is safe. That is, whether you have a safe sequence, whether if a safe sequence exists. So if we find that a safe sequence exists even in this new state, then we can physically allocate the resources. Okay. So then only you go for the physical allocation of resources. But if you find that this new state is not safe, in that case you cannot allocate the resources. So you have to restore the previous state by again modifying these data structures. That means you have to put these data structures to the previous values. Okay. So now what we need is another algorithm to check whether this state is safe. That means whether we can have a safe sequence. So for that, there is another algorithm which is called a safety algorithm. The safety algorithm makes use of two more data structures. One of the data structure is called work, which is initialized with the value of available, and another data structure is finish, that is a Boolean vector, and all the elements of finish are initialized to a value false. Okay. So this is the initial step of the safety algorithm. Okay. Now once this initialization is done, in the second step, what you have to do is you have to find some process, okay, find some process in the set of processes for which finish I equal to false and need I is less than or equal to work. And as we said that work is initialized to available and need I is the future requirement of the process. Okay. So if I find that there is some process which is not yet finished and the future need of that process is less than or equal to available, that means with the set of available resources till now, that process can complete operation. So what I will do is, for that particular process, I will set finish equal to true, and I will check it again and again until and I reach to a condition that the finish for every process, every component in this vector finish becomes a value true. If I can find that in some order, every element in this vector finish can attain a value true, then the state from which I started this, that is a safe state. But if I find that there is at least one process for which this finish vector cannot be made equal to true, that process cannot be completed. So that may lead to a deadlock and the state will be an unsafe state. Okay. So the complete algorithm will be like this: find an I, that is find a process Pi I such that finish I equal to false and need I is less than or equal to work. Okay. If there is no such I, then go to step 4. In step 3, what we do is, we have found an I for which finish I equal to false and need I is less than or equal to work. So I assume that that process can complete operation. If the process completes its execution, then it will release all the resources which are allocated to it. So those resources will now be able to will be added to the available number of resources. Okay. So here what I do is work, because work in this safety algorithm gives the number of available resources. So we make work equal to work plus allocation I. That is the number of resources which were allocated to the process Pi. So work is equal to work plus allocation I, and the corresponding finish I make equal to true. Okay. Then you go back to step 2. That means I have found one process which can be complete. Then I have to find out whether there is any other process that can also be completed. And these steps between 2 and 3 will be repeated until and unless this condition is satisfied. That is, if no such I, then go to step 4. And in step 4, what you do is, you check whether every component in the finish vector is equal to true or not. If every component in the finish vector is equal to true, that means the state is safe. Okay. So in step 4, what I do is I check if finish I equal to true for all I. If finish I equal to true for all I, then the system is safe. Then the okay. Else the system is unsafe, and from here you go back to this previous algorithm. Okay. Here you check if this new state is safe, if a safe sequence exists. Okay. So when I find that the system is safe, the sequence in which, or the order in which this finish I was made true, okay, it may so happen that first I find that for P5 I can make finish 5 equal to true. Then finish 1 can be made true. Then finish 3 can be made true. Okay. So the order in which the processes can apparently complete their operation, that particular order of the processes is called a safe sequence. Okay. And if I find that finish I, for some I, finish I is not equal to true, even in step 4 of this safety algorithm, that means I cannot have a safe sequence. Okay. So if there is no safe sequence, the system is unsafe or the state is unsafe. If there is a safe sequence, the state is safe. So if the state is safe, then you can physically allocate the resources. If the state is not safe, then you don't allocate the resources physically. Okay. However, as I said, that it does not mean that state unsafe means there will always be a deadlock. State unsafe means that state may lead to deadlock. But if it is safe, it will never lead to deadlock. So what this deadlock avoidance algorithm does is, it does not put any restriction on the way in which the requests are to be made. The requests can be made by any process at any time for any number of resources, provided that does not contradict its own declaration. Here, at any point of time, request I cannot be greater than need I. So initially, when the process is starting for the first time, the allocation vector is 0 to the process. That means need I will be equal to the max I as declared by process Pi. Okay. So by putting this condition, I always ensure that the process never requests for resources which is greater than the maximum requirement as declared by the process. Okay. So that is the only restriction, and this is quite logical restriction. Okay. So here in this algorithm, in this deadlock avoidance technique, what is tried to do is the system always tries to find out that whenever a process puts a request, whether the request can be immediately granted or the request will be delayed. That's all. But there is no restriction on the way in which the resources can be requested. Okay. And this is called banker's algorithm simply because the same algorithm can be used by the banking people to mobilize their resources, that is capital. Okay. It may so happen because banking people, they give loan to a number of customers. If you add up the requirement of all the customers, that may be more than the total capital that the bank has got. That is quite possible. But the requirement of individual customers is less than the total capital available in the bank. Okay. So that being the situation, they also have to make use of some criteria by which the loans are to be allocated. Okay. So this is the same algorithm which can also be used by the banking people to grant the loans to different customers, so that the bank will not be in trouble. Okay. So that is the reason it is also called banker's algorithm. Okay. So we have seen two techniques, two ways of dealing with deadlock. One is deadlock prevention, other one is deadlock avoidance. Next day, we'll take an example on this deadlock avoidance technique. I think that will give you, clarify many of the doubts that you can have in this algorithm.